continue. All right, so make note of that. I missed the first few slides there. Sorry about that. All right, liquids are not compressible. Again, you recall the diagram of liquids, they're pretty close to each other. So there's not a lot of room to come into each other again, which is a good thing. If you think about it, you would not have power steering, power brakes, or heavy equipment would not function because they use hydraulics and they're using oil and liquid to give us this power to be able to do things that we couldn't do. If you ever driven a vehicle with no power steering, it's a tough thing to get it turning that steering wheel or even power brakes. I know some of you may not be familiar with that, but there was a day when you didn't have power steering, power brakes, or even air conditioning in your vehicle. Liquids have a much higher density than gases with respect to gases. And again, density is that ratio of mass over volume. Okay. Now, when liquids are soluble with each other or miscible, I got two liquids, they will mix uniformly. And so if I got, soda pop, it's a mixture. I got all the ingredients for, my Coke, but it's all in water. It's all homogeneous mixture. Okay. Now with gases, guess what? Gases have no shape. They take the shape of their container, like liquids. Okay. And because the molecules are far apart from each other, there's a lot of open space. They can expand and they can compress. Okay. So as the volume increases, the atoms get further apart. Makes sense, doesn't it? Volumes decrease, atoms get closer together. Okay. And they don't have a set volume. We tell you this right now, but we will learn down the road, a few chapters down the road, that gases only under certain conditions have a known volume. But from this point right now, they don't have a set volume. Okay. They tend to have low densities. You can see the numbers there, very, very small, 0.001 grams per milliliters, that ratio again, mass over volume. And gases, they tend to mix completely with each other. Typical, our air that we breathe made up of roughly 78% nitrogen, 21% oxygen, carbon dioxide, and a series of a bunch of other gases, okay? They exert a pressure. Why? Because they're hitting the sides of the container. Your tires have a pressure, right? 32 PSI, pounds per square inch. If they get less than that, what do? You go to Quick Trip, Circle K, you pump it up with air. You put more matter, gas molecules into the tire, and now the pressure goes up because now you have more matter in there hitting against the sides of the tire. Pressure goes up. Okay. All right, so basically, to kind of summarize all this is solids have a fixed shape. That is correct. And they have a fixed volume, solids. Liquids, on the other hand, do not have a fixed shape. They take the shape of whatever container they happen to be in, but they do have a fixed volume. Okay. Gases do not have a shape, and they do not have a fixed volume. In both cases, they take the volume and they take the shape of the container that they're in. All right, some physical and chemical properties. Now, there's a difference in chemistry between a physical property and a chemical property. All right, and you're well familiar with physical properties, and I go back to water, right? Because water has a formula we're all familiar. We all say H2O. That is the formula of water, and we're going to learn more about this formula or how to write formulas, but I can write them with this H subscript 2O. That is the formula for water, telling me that there's 2 atoms of hydrogen and 1 atom of oxygen. Okay. Now, water is very interesting because it's very important, but it's very interesting. When we take water, liquid water, and we freeze it, we form ice, obviously. We're all familiar with that. but we didn't change the formula. H2O is still H2O when it's frozen in ice cubes, and is H2O when it's liquid. And if we take that water and we put it on the pot in our kitchen and we're going to make some spaghetti, we're going to boil some spaghetti, we're going to hit that water with energy, warm it up, and then we're going to boil it. It's going to vaporize, and now we have water as a gas. Also, in that condition, when it's a gas, it is still H2O, okay? We have not done nothing to change the chemical formula for water. That, ladies and gentlemen, is a physical change. You can go from one state to another, but the formula remains intact. Okay. Now, before I go further, a chemical change is you totally change the formula. Case in point, very simple example is your vehicle. You put gas in your vehicle. It is a hydrocarbon, what is called hydrocarbon. It runs through the engine, it gets ignited, it burns, okay? As it burns, it gets converted to carbon dioxide and water. It's no longer that hydrocarbon. That piece of wood that you're using, maybe that briquette to do a little barbecue, you light it up, it converts to something else, okay? It's no longer a briquette, it's something else. And that is a chemical change because the chemical structure has completely been changed when it comes to a chemical property versus a physical property, okay? Now, with respect to properties, it's basically things like describes the appearance of the chemical. Facts about the chemical, like its color, it's blue color, yellow color, no color, clear, brown, white, whatever. It may have an odor. Specific odor. A lot of the mints that you ingest, to give you breath mints, those are compounds called esters. They smell very good. Banana, the banana odor, that's an ester. Okay, smells very good. Okay, taste is very specific. Some things taste specific. They're good. All right, like bananas again. that is the texture. What do we mean the melting point? Well, that is the temperature in which that chemical, if it's a solid, melts. Analogous to, let's say, a stick of butter. It's solid and you put it on the pan and it melts. That's what we call the melting point. Now, the physical state, it could be a solid, a liquid, or a gas relative to some temperature. And normally we're talking about ambient temperature, which is room temperature, roughly 25 degrees Celsius. And so we know that stick of butter is a solid, okay? But with time, guess what? It melts, becomes a liquid, right? We know that water at room temperature is a liquid, but we stick it in the freezer, we drop the temperature, it becomes solid. We heat it up, it becomes a gas. So the physical state is relative to a set condition and normally to ambient temperature. Density is a physical property. Solubility, is it soluble in water or is it more soluble in the oil? Okay, we're going to talk about this and how we're going to be able to determine solubility, whether in oil or in a water. Conductivity, does it conduct electricity? Okay, like copper wire. Copper wire conducts electricity. Okay, that's a physical property of copper. And hardness, there are physical properties of solids. A good example is carbon. Carbon can be a graphite, which is very slimy, and it's not very hard. Or carbon, depending on how it's structurally relative to each other, can become a diamond, the hardest thing on earth. All right, so. All right, so that's physical properties. Now, compared to chemical properties, it describes how a chemical reacts or behaves. Something that's flammable. A lot of the alcohol is flammable. A lot of the gases like butane, propane, it is flammable. Those are the chemical properties of those compounds. Or they could be explosive, like TNT, AKA dynamite, very explosive. It could be toxic, very poisonous, or it could not do anything. Inert gold, pure gold, is pretty much inert because it's not very reactive. When we dig gold out, it's just as shiny now as it was, 10,000 years ago, because it doesn't have a lot of reactivity. It could be reactive. Sodium metal, extremely reactive. I put that in water, it reacts very quickly. Irons, it rust. Rust is a chemical process. I used to have a pickup truck, had a lot of rust, a lot of chemistry involved there. Okay, because it's being oxidized, or it will decompose. A lot of chemicals, when you heat them, they don't melt, they actually decompose and break apart into different chemicals. So those are chemical properties versus physical properties. Now, the physical changes, you're familiar with these. I'm not telling you something you don't already know. Solids, you may have a couple of physical changes that you may not be familiar with respect to naming them. Solid to liquid, what do we call that? It's called melting. Okay, this stick of butter, we heat it up, goes to liquid, we're melting it. Or an ice cube going to liquid becomes, that's what we call it. It is melting. When we take a liquid and we make it go into a gas, what do you think? Boiling, or even at that, evaporating. Okay, so you're taking that liquid and it's going into the gas phase. When we take a gas and we make a liquid out of that. Okay, so imagine this. I got a gas, which is out there in the atmosphere, and then we do something to it and we make it into a liquid. We actually compress it. We call that condensation. Think about this for a minute. You got a nice cold drink right now. Okay, I got some soda pop running here. The outside of my soda pop is wet, moist. Where's this moisture coming from? Any ideas? We call it condensation, but where is it coming from? It's not any Harry Potter magic there. Trust me. Okay. Where's this liquid from the outside of my container coming from? Yeah, the atmosphere around it. Oh, we got an answer. Maybe temperature change. That is correct. It's a temperature change, but because of the temperature change, where is the H2O on the outside of this container that I have here? Oh, there it is. I got H2O coming out here because I have a nice cold drink. But where is this water coming from? This liquid? It is correct because of a temperature change, because it's colder on the outside. And we all know we call this condensation, right? It's coming from the air right around me, because around me we have humidity. Now, granted, Arizona, we don't have high humidity. That's correct, Jose. It's the air around us. So the humidity is nothing more than H2O in the gas phase. Okay, and it's full of energy because the molecules are separated from each other. And so what happens is, as those molecules hit the outside of my container, that cold container takes that energy away from the molecules that are in the gas phase. And it basically calms them down because they're high energy on there. So they calm them down. And what's happening with time, more molecules come in together, the energy is taken away, and they condense and they go back to the liquid phase. Okay. And so I once had a person tell me that it was diffusing from the liquid inside outside. No, that's not happening. Okay. Not that it couldn't happen. The plastic is, even though we see it holding liquid, but over time that plastic is porous and liquid can get through there, but it would take a long time. Okay. So we call that condensation. All right. So far, nothing different that you're already familiar with. We got a liquid going to solid. We got liquid water going to solid. We're making ice cubes, right? Freezing. Okay. And then if we take a solid and it goes to gas, this may be new to you. Okay. But you may have seen it, and I'm fairly sure you've seen it. We call that sublimation. Classic example here would be carbon dioxide. If you go to Fry's and you ask for dry ice, you'll get some chunks of white material in this fume coming out. You'll be making this little smoke. All carbon dioxide all dry ice is carbon dioxide that is a gas that has been condensed and brought together. So you put a lot of pressure in the carbon dioxide gas. The molecules then start attract to each other, and they start condensing and forming a solid. But it's unique in that dry ice goes directly from the solid phase to the gas, bypassing the liquid phase. And that is what we call sublimation. Dry ice is one example. Another one would be mothballs. You may be familiar with mothballs. Some people use them in their closets to get rid of all kinds of closet bugs. Okay, that is another solid that goes directly from the chemical that goes directly from the solid phase into the liquid phase. Okay, so if you want to help your plants, FYI, get you some dry ice if you got a lot of plants at home, and then put them around your plants. Why? Because that's carbon dioxide, which is good for the plant. And then the plant will reward you by giving you oxygen. Okay, so we have a symbiotic relationship here with plants. All right, don't put it on the plants and you're going to freeze the roots, and that's not good. Put them around it. All right, now going from a gas to a solid, okay, and it's the opposite. This is how they make dry ice. You take carbon dioxide, a gas, and then you convert it back to the solid, and that is called deposition. Okay, deposition. So we got melting, boiling, vaporizing, evaporating, condensation, freezing, sublimation, and deposition. These are the physical changes that occur in the states. Now let's go back very quickly to liquid to gas, evaporating. Okay, so we all know that you can take a container of water, a glass of water, leave it on your kitchen top for about a week, and what happens? You come back, liquid may be gone, right? Okay. Well, wait a minute. How did that happen? How did that happen in that the liquid totally evaporated? Because we know that I can get a pot of water, heat it up on the kitchen top there and boil it and evaporate that. But why did that glass with water disappear and go into the gas phase with no energy placed into that container? What happened there? More Harry Potter magic, right? Yeah. Why? What is happening there? Well, the liquid molecules, the atoms in the liquid phase, though they're not as organized as I said earlier, they move around. If you go back to the diagram, of the of the liquid, and we had, I don't know, it looked like something like this. It wasn't very ordered, right? Okay. Well, these atoms are moving. Okay. And guess what? These guys are moving, and one of them can come over here and knock one of these. This is the surface. This is the top of your liquid. Okay. And so one of them can come in with enough energy and transfer that energy to another one. And guess what? Kick this guy out into the gas phase. Just by virtue of these atoms moving around, because atoms move around, they're not, and this is an example of how we know that atoms are moving, because stuff evaporates. And it's not magically evaporating. It's simply because these guys, it's like shooting pool here. Right? This guy comes here and smacks into the one on the surface. He picks up enough energy to get out of the liquid phase and into the gas phase. And with time, this happens to all of them. So you end up with, you come back a week or two later, that glass of water is totally evaporated. It's totally gone. Right? Because it evaporated because the energy of the movement of the atoms knocking into each other, forcing some to go into the gas phase. Now we have letters to depict the physical change, and those letters were S for solid, L, lowercase s, lowercase l, and lowercase g, and we put those in parentheses. So here's an example of a process, be it a physical process or a chemical process. Okay, like for example, if what we do in chemistry, we want to depict something that's happening. We'll say maybe A plus B, and then we draw an arrow, and then we say, I don't know, let's say this thing made C. Okay. Well, this arrow tells us it's something's happening, be it a physical or a chemical change. And to the left of the arrow are what we call the reactants. Okay. Those are the guys that come together and something's going to happen. And to the right of the arrow, whatever happened, what we find are the products. Okay. And this arrow depicts a one-way arrow, meaning everything went from left to right. FYI, down the road, we can have examples where we have a double arrow, where a chemical process or physical process can occur in both directions, okay? Hence this here, where we have a liquid going to a solid, going to a liquid, then going on to the gas, or we can reverse the process, okay? Normally, for a chemical process, a physical process, what was happening here is we are either adding energy into the system or taking energy out to cause things to go into different physical states. So if we look at this reaction here, or this process, I should say, okay, we see that we got H2O, water, and then in parentheses, gives us the letter L, which tells us it's in the liquid state. Then we got the arrow telling us a process occurred, okay? And guess what? Look at the formula, H2O. Nothing happened to the formula. The formula still is the same, H2O. The only difference is now its physical state has changed, okay? And we got G in parentheses. So what that tells you is this. I may not know what the formula is, H2O, it's something, but I do know that the physical state would simply, I know two things. One, the formula, either as a reactant or as a product, remains the same, okay? Oh, that tells me a physical process. And then to compound that, to aid you even further, you can see that the physical change went from a liquid to a gas. So this is an example of a physical change. We're going to give you an example. Now, another one. If I take water and I hit it with electricity, guess what? I can break it up. I can break it up into hydrogen and oxygen separately. That's why it's so important we find water out in space, because we can use hydrogen for fuel and oxygen to breathe, right? Okay, and see here, we totally broke up the molecule of H2O. So this example I wrote down here would be an example of a chemical. Excuse my writing here, my resolution on my little pad sometimes acts up and the writing comes out looking weird. So here on this side on the left, we got a physical change. And I saw that simply because I looked at the formula and they didn't change as a reactant going to a product. Then I looked at the physical state and it actually went from a liquid to a gas, okay? Just by analyzing the equation, okay? And fortunately here, it's a simple water, But you could be given any equation and just analyze it. And we'll have some examples of it. You may not know what the formula is, what the chemical is, but you can analyze how the equation is written. So you can determine whether it's a chemical or a physical change. All right, so that example here is water boiling. This diagram kind of puts it all together, where you got sublimation, where you got solid going directly to gas, and then you got gas taking energy away, giving you deposition going back to solid. The physical changes that occur here are driven by energy. Chemicals have energy just by the nature of the beast, if you will. And whatever we do to remove that energy, we can change its physical property, okay? And all this is the interaction of molecules with each other. Solid, they interact very much together and strongly with each other. So they're solid. And then if we break up that interaction a little bit, we can convert that to the liquid. We're taking that energy away from a solid and taking away the interaction between the molecules to get into liquid. Ask yourself a question. All right, we just talked about honey, right? And water. Obviously, water will flow quicker. How can I make that honey flow a little bit quicker? As fast as water. What would you do? Now, other than diluting it, let me qualify that. Other than diluting the honey, but let's take a cup of honey and a cup of water. How can I make that honey flow as fast as that water? What would you think would be a most logical thing to do? Anybody want to take a guess at it? Mix the both? No, don't mix the both. You can't mix them. Okay, I got a cup of water and a cup of honey. We know, or you have seen, that if I take that cup of water and I empty it, it flows at a certain rate. If I take that cup of honey and I empty it or do it together, you know that that honey is going to take longer to empty that container, right? It's like the ketchup. Remember, there used to be an old commercial about ketchups and how one flows slower than the other. Okay, but how can I get that honey when I rotate both cups to flow as quickly as water? Change the physical state.
Could you boil it?
Heat it, exactly. London, you got it there. Would heating the honey help? Of course, yes. By heating the honey, you break up that interaction between the molecules and you break up that attraction. That's what makes honey want to not flow, because the molecules are attracted to each other much more tightly, if you will, stronger than the water. And we're talking about these forces that are occurring within the molecules here. Okay, let me draw it bigger. We're talking about these interactions here between them. If that's a very strong interaction, it would hold on to each other. Anyway, yeah, it's correct. Heat it up a little bit, that honey is gonna go. So this table here is nothing more than in the physical state going from point A, from solid to gas, solid to liquid, or liquid to gas. It's a function of removing energy or putting energy into the system. All right, so we know that atoms are always moving, even in the solid state. They are moving around within the solid state. We'll learn about these atoms and how they're bonded to each other, and these bonds are moving. Okay, so when you heat the ice, obviously the water molecules gain energy. They gain what we call kinetic energy. That's movement energy, and they're going to move faster. They're going to start moving around a little quicker. All right. And if they continue to gain energy, that energy that they gain will break up that attraction that they have for each other. And therefore, here, the solid will begin to melt and go into the liquid. Just like that stick of butter. Okay. You take it out of the refrigerator. It's a nice solid stick, right? You put it on the on a pan to cook something up. You put a little swab, put it in there. What happens to that butter? It starts to melt, right? It goes into the liquid phase. And you're putting energy into the system. You're causing the molecules to move a little faster. And eventually they have enough energy that they're going to move away from each other rapidly. All right. So again, we continue to heat, you go into the gas phase. And that's basically, again, here showing you what's happening in a different type of diagram. It's all function of breaking up this interaction between the atoms of the compound. Now, as I mentioned earlier, in all these, in the physical changes, okay, let me make sure we understand here, and we're take away. This could be solid ice, H2O, okay? When we heat it, we make liquid, H2O. We continue to heat it, guess what? We have H2O. So physical changes does not change the structure or the chemicals structure of the compound, molecule, or whatever you're using here. Water is still water. If it's an ice cube, it's still water. If it's a liquid, and it's still water as a gas phase. Okay. That's something we have to make sure we take away from physical changes. When we get to chemical changes, we are literally breaking the molecules apart. Physical changes, we're breaking the molecules' interaction with each other. For chemical changes, we are breaking the individual molecules totally apart and rearranging them to make something else. Okay. The formula changes, and we call these chemical reactions. And remember that when we get to chemical reactions, there's only 6 of them, 6 types of chemical reactions. All right. The starting material that we utilize is literally destroyed, and we make a new material with totally different properties, completely. An example, as I stated earlier, was burning gasoline. Gasoline is what we call a hydrocarbon. We call it hydrocarbon because it's made up mostly of just carbon and hydrogen in the structure, and they're flammable. And we use this general equation where we see C subscript X, H subscript X. X is a number. X is a variable number. So that's why you put X here. The smallest one here would be C, where X for carbon would be 1 and H will be 4. That's the smallest hydrocarbon. That's called methane. We're all familiar or heard about methane. When we burn a gas, we need oxygen. Anything we need to burn, right? We need oxygen. So oxygen is a reactant. In fact, this is a good example of one of the 6 reactions. And so we have a hydrocarbon and we have oxygen, okay? Without oxygen, nothing burns. And the only 2 materials that for us at Chem 130, the only 2 materials when you burn a hydrocarbon, the only 2 materials that you make product-wise is carbon dioxide and water, okay? Yes, we know that if you burn the fuel, you're going to get carbon monoxide, okay? Notice the difference. Here's carbon monoxide. This is called carbon dioxide. A little introduction to the names. Carbon monoxide meaning 1 oxygen, carbon dioxide meaning 2 oxygens. We know that carbon monoxide is a poisonous gas, and our vehicles generate that. And the only reason it does that is because our car engines are not very efficient. They're lousy efficiency, don't burn well at all. So we do make carbon monoxide as a product. But we're going to talk about ideal conditions. So anytime we burn a hydrocarbon, we only get carbon dioxide and water. In fact, if you're driving around and you look at a tailpipe of a vehicle in front of you, occasionally you may see some liquid dripping out of its tailpipe. What that is guess what? Water, okay? That you see there. All right, let's clear this up. So note here what happened. We have totally destroyed that hydrocarbon and created two new compounds, carbon dioxide and water. Now, what indicates a chemical change? Okay, a couple of things like oxidation of matter, things like obviously burning. Burning is oxidation, or something that rusts. If you got an old pickup truck, like I did, old truck I had before, it had a lot of rust, a lot of oxidation of matter on that thing. Okay. It can release bubble gases without giving off heat. Okay. So it will spontaneously bubble. And bubbling is a good indication of a chemical reaction. Classic example, Alka-Seltzer. Okay. Alka-Seltzer is a pretty good setup here. Alka-Seltzer, if you read the label, you'll see it's got a little bit of citric acid, which is an acid, and a little bit of bicarb. Okay. And so when it goes into the water, the acid and the bicarb react. And one of the products of sodium bicarb is carbon dioxide. So it tends to bubble up. So medicinally, I'm not aware of any medicinal aspects of carbon dioxide bubbling in Alka-Seltzer to assist you in your health issues that you're taking it, but the other active ingredients do that. So the bubbling just, I guess, just mix things up. Well, anyway, release of bubbles with not giving off heat, not boiling. Okay, you might get two liquids and you put them together, and the thing precipitates. It forms a solid. A lot of chemical tests are used that when we're looking for the presence of, say, chlorides. We have a little test that we can do. We put your water sample in that material, and guess what? You form a solid. That's a good indication of some chemical. It could release heat. Okay. Good example, you go to the pharmacy, you go buy a hot pad or a cold pack, right? You may have used one. Get the pack, smack it up, break the chemicals inside so they can mix with each other. And guess what? One of them may give off heat, get warm, and put it on your muscles because you got sore muscles. Or another one may get cold. Okay. So it may release heat or it may get cold. Or light may be given off. These glow sticks are a good example of that. You take them, you break them, you get this light. That is an indication of a chemical reaction that may have proceeded. And of course, you might get things change in color. It may go from a blue to no color or vice versa. Or you may get an odor, either a good one or a bad one. Like I mentioned earlier, esters like wintergreen, they're made up of what we call an acid and an alcohol. Separately, they smell bad, but when you put them together and mix them up to form the ester, they smell pretty good. Wintergreens, banana oil, things like that. Or you can get some chemicals that are sulfur based that when you mix, oh man, it smells pretty bad. So odor is a good indication. Okay. Here's an example of a chemical change. And also an example of the power of electrons. One of the reasons that I kind of really fascinated me with chemistry. All right, we have two things here, two reactants here. We have sodium metal, okay, which is a picture of it. It's a solid metal. This is an element. It's not the sodium that we think of, we put in our French fries, okay? Now, sodium is a very reactive metal. You wouldn't put that in your mouth because it would react with the liquid, the water in your mouth, and generate the gas and a lot of heat, and it will give you blow up in your mouth, basically, okay? So it's the element sodium is very unreactive and very hazardous. Chlorine. Notice we have a subscript here. We'll learn more about that in other chapters. Chlorine is a poisonous gas. Okay. It's here. We got it in the form of liquid, but it gives off some of that chlorine gas you may be familiar with. It's that chlorine odors you find maybe with a lot of municipalities, water treatment plants may use chlorine to treat their water to get rid of bacteria and so forth. And if you live by one of them, if you ever see a yellow puff of smoke, get upstream quick, because this will really play havoc on your lungs. So we got a hazardous metal and we got a poisonous gas, and they react and we create sodium chloride. Notice the formula here. Sodium chloride. Okay. This is something you can put on your French fries and it won't blow up in your face. Now, the only physical hazard you may have is if you have high blood pressure, you may not the best thing to take, right? And the only thing that happened between going from here to here, there was a transfer of two tiny electrons, that were transferred to create sodium chloride, salt. So point being here, this is an example of a chemical change. We took two chemicals and created something new, totally different product, okay? Totally different product. All right. Now, here, question is, well, do we know it's a physical or a chemical change? And granted, at this point, you may not know what NH3 is. We understand that. But you can see that NH3, number one, is still NH3 as a product. So what does that indicate? Got to be a physical change, right? We didn't do anything to the formula. NH3 as a reactant is still NH3 as a product. Even though you may not know what it is, but I'm going to tell you what it is. I'm glad you asked. If you ever wash windows with some window cleaner, you'll use this. It's called ammonia. If you ever have diapers, wet diapers from a baby, and they sit there for a few hours or days, you smell that ammonia. That is the formula for ammonia, okay? But notice NH3, what that means is the way it's written is there's a nitrogen. Normally the first atom that's written is the central atom, and then there's three hydrogens written, bonded around the nitrogen. But we'll get into that with time, trust me. Okay, so, but NH3 is still the same as the reactant and as a product. And then furthermore, it tells me I went from a gas to a liquid. Therefore, guess what? I got a physical change, okay? And this is what I'm talking about. Looking at which problem you got and analyze it, break it down, okay? I know you notice these numbers up front. We won't talk about that now, but you will learn at length why we got numbers up front. It's related to conservation of matter. Okay, here we got NH3 again. Okay, and we got the reaction, and guess what happened this time? We totally broke it up. In fact, what tells you that is this plus sign. That means I got two products here. I got nitrogen and I got hydrogen gas. Totally broke it up into two different products. That would indicate a chemical change. Okay. Now, the next one. Let's take a look at the next one. Let's break it down. Well, I don't know what H2O2 is, but I will tell you here in a bit. Okay, and you have used this before, I'm pretty sure. But again, like number two, I make two different products. In fact, I make here what's called hydrogen, and I make oxygen, and make two different products, got a plus sign. FYI, H2O2, if you ever had a cut, or you may use it to whiten your teeth, or you may use it to color your hair. Anybody know what that is with all the hints I gave you? Hydrogen peroxide. Okay, that's the formula for hydrogen peroxide. And it's totally broke up. Okay. And so being that it totally broke up, guess what? I got a chemical change here. Number four, I got H2O2 again. Okay. And I look at the product side, I got H2O2 again as a product. That in itself should tell you physical change. And then to further nail it for you. You got a liquid to a solid. So it went from a liquid to a solid. It froze it. It underwent freezing. So that is a physical change. And then the last one, again, C6H6. We don't know what that is, but I'll tell you what it is. But it stays the same. C6H6 as the reactant is still C6H6. That's another hydrocarbon, what we call hydrocarbons, because it's made up of nothing but carbon and hydrogen. And the fact that the formula remains the same tells me that it is a physical change. That is called benzene. Benzene is not a good chemical and it does cause cancer if you're subjected to it for long terms. All right, let me clear this up a little bit. Let me try it. So what we're going to talk about now is an element, compound, and we're going to talk about mixtures. Now, elements are one type of atoms only. Our periodic table, those are elements, okay? There's 118 elements. Periodic table is recently, last couple of years was full. Right now, scientists are working on more to fill this periodic table a little bit further, okay? Now, elements are one type of atom and they can't be broken down to anything less. If you break down an element, which you have broken them down to, are into the subatomic particles. You've broken, and we mentioned this in the beginning. The subatomic particles that we're going to work with are the proton, the neutron, and the electrons. So if you break an element down further, then you get into the protons and the electrons and the neutrons, and those are just subatomic particles. It's not an element. We do have some elements, specifically only 7 of the 118. We have some elements that we call diatomic, right here, diatomic. And the reason they're diatomic is by themselves, they're not very stable. And there's only 7 of them, and we'll demonstrate, show you which ones they are. But oxygen gas is one, hydrogen gas is another, nitrogen is another one. We introduced those earlier in the previous example. But they're diatomic, they're still elements. They just happen to be diatomic because here on Earth, they're not stable by themselves compared to the other elements that by themselves, they're stable. Okay. Now, with respect to a compound, now here's the difference here between the element and a compound. A compound, which is what are the chemical compounds that we're going to be working with, are made up of 2 or more different atoms bonded together. The earlier example, we had sodium chloride. Okay, when we reacted sodium and when we reacted sodium plus chlorine to give us sodium chloride. Notice here, chlorine, one of the diatomic elements. They're both made up of 2 chlorines. Sodium is all by itself, just sodium. But sodium chloride is made up of 2 different elements. It's made up of sodium and chlorine. Okay, and it has a specific name. We'll learn about that. So that sodium chloride is an element. You could have potassium chloride, magnesium chloride, calcium hydroxide. If you eat Tums, that's what you're eating. Those are our compounds. H2O, water, is a compound. It's made up of 2 different elements. Okay. And then mixture, pure, obviously, if we can have a pure element or a pure compound. And that's basically just, it's pretty self-explanatory, right? Something is pure, there's nothing else but whatever that material is. It could be all elements or it could be all compounds, okay? Because once we get a pure material, we can't make anything else and we can't separate it into different components. as an organic chemist, when we make a new compound, that stuff was not pure. We would have to go through a process figuring out what's the best way to purify it, to clean it up. A good example would be sugar. Sugar that comes out is not very pure. Okay, so you gotta go through a process to separate all the other gunk from sugar to get you that nice white crystalline looking sugar material. Then of course we got mixtures. You know, we could have mixtures where we have two or more particles mixed together, two different ones. It could be a mixture, it could be a mixture of elements. It could be a mixture of a compound and the element, you know, any combination thereof. Okay, so they're just totally different materials. And so we have a flow chart here to help you out a little bit. We got matter, whatever the matter may be. We go to the right, we got a mixture. And that's denoted down here. You can see the circular dots here, two different colors. On the left side, got a dark one and two that are together. Here's something to take away from this one. I mean, notice that these two that are together, that should indicate to you they're together and they are the same color and the same size. That indicates a diatomic material. Diatomic meaning there are two elements put together. That could represent oxygen, O2, or hydrogen. We talked about those being diatomic. The dark ones here, obviously they're all by themselves. It's just simply an element, okay? But the fact that we got diatomic red and then a single element dark, we got a mixture. We look to the right, same scenario. We got three different colors of the circles here. We got a mixture of three different elements, okay? I guess the green one, the red one, and the dark one. Now, on the left side, we get the pure substance. Well, we can have either a pure element or an atom, like over here, where just all you see is the red circles. That could represent neon. That's what Ne is, neon. And then to the right, again, here's the diatomic ones, or two of them together. All the diatomic molecules or atoms are called molecules. So you have a molecule of oxygen, a molecule of hydrogen. They are elements that happen to be diatomic, okay? Now with respect to compounds, now remember the definition of compounds is a combination of two or more different elements, okay? And normally you have a central atom and then the other atoms are bonded around the central atom. And if you notice, it looks like upside down Mickey Mouse ears, where you got the red circle and then the three yellow dots, okay? That tells you that the central atom is a red one, which could be oxygen. And then the two yellow ones could be hydrogen. And so, this is a good example. Maybe that could be H2O, or AKA water. Okay, and then we got sodium chloride. Obviously, it's a compound. You got two different colors. All right. Here. Let me see one more. Okay. Well, I tell you what, I got 2:15. I'm hoping to get a little bit further, but it's okay. All right, we are at slide number 26. Let us stop here. We will continue. We'll definitely finish this on Monday, and then we will jump into chapter 2, and then obviously we got to knock out the other chapters before the first exam 1 through 3. So shouldn't be a problem. All right.